Hello everyone, in this video we're going to look at some applications of quadratic equations. Our strategy for solving word problems containing quadratic equations will be the same strategy that we use for solving any word problem. There's going to be a three-step process involved here. Of course, each step may have some sub-steps. So the first thing is to make sure you understand. Now, this sounds simple enough, but it's the most important step because it's in this step where you either start the process in the right way or not. So, and of course, sometimes a problem is very simple. You may be able to read it once and know exactly what these two questions are: what is given and what is wanted. That's exactly what you need to determine when you read a word problem. Once you have figured this out, and of course in the process of doing so, you can use diagrams, tables, etc. to organize the information that's given, because what makes a word problem a little bit more challenging than just a regular equation or something like that is that with, say, a certain equation, no matter how complex it is, if you're trying to solve it, all the information you need is in one place. Whereas in a word problem, some piece of the information may be given in the first phrase, another one in the third sentence, etc. So the problems pieces of information are scattered all over the place. So we want to organize the information. Second thing we'll do is we'll go ahead and translate. If we've done this step well, this should be an easy transition into the next step. Translate, of course, not from English to French or anything like that. We're going to translate from, at least in this class and in this country, from English to mathematics. I see that I have a typo here. We'll just fix that. Once you have completely understood what is given and what is wanted, we're ready to choose a variable and set up either an equation or an inequality. In most of the problems we're going to be doing together, it's just going to be an equation, but sometimes an inequality is more suitable. Now, when we go ahead and set that up, the final step is the easiest step because this is just going to be solving the equation. Now, sometimes solving that equation will directly answer what is wanted here. Sometimes you have to do a little manipulation. For example, maybe you're dealing with a triangle and you found one angle, but they actually wanted another angle, which you can easily answer and get. Or maybe you were dealing with the number of males and females in a given room or some conference, and you found through your equation the number of men, but they wanted the number of, say, women in the conference. And again, it would usually be a very simple step to getting that, but you have to make sure that you answer the actual question that is asked, not whatever your equation generates as a solution. And also, your final answer should always have the proper units attached to it, if applicable. So here's a simple enough number problem. There's not going to be any units involved here because we're just dealing with numbers. It's just good practice. So the product of the post office box numbers of two consecutive mailboxes at a post office is 132. Find the number written on each box. Now, usually, if you've been to a post office, you have boxes one right next to the other. I mean, they're very standard. Each goes up by one. If this is box 3, the next one is 4, 5, etc. So now we're told that we have two post office boxes right next to each other. So scenario like this, right? And we don't know what the number on either one is, but we do know that their product is 132. So for example, if we let the first one be x, the next one will be x plus 1, right? Because as we said, they're handled pretty traditionally. All right. Now, by product, of course, notice this is when we're doing a diagram, we're trying to understand what's going on here, right? Now they tell us the product of these two, the numbers on these two boxes is 132. So that should be a pretty simple translation for us. X times x plus 1 equals 132. Okay, so now it's a matter of simply solving this equation, which shouldn't be too difficult for us at this point. All right, so we're going to follow the procedure we learned in our previous video, which is we're going to basically simplify both sides first. So here we'll just distribute x squared plus x equals 132. We're going to move all the terms to one side because this is a non-linear equation, given that there's a degree higher than 1 in it. So the procedure is to move everything to one side and then make sure we just have 0 on the other side. Now we're going to go ahead and factor this quadratic trinomial. Of course, 132 is a pretty large composite number, so in order to make it easier for us to see what the two numbers that should go in the factorization are, we will go ahead and look at the prime factorization of 132. The smallest prime number that goes into 132 is 2. We'll write that here and then we'll divide. 132 divided by 2 is 66. And then again, we'll ask the same question. What's the smallest prime number that goes into 66? Of course, that's 2. We'll write it next to it and we divide, so we get 33. And then this time 2 won't work anymore. We have to move up to 3. 3 goes into 33 11 times, and then 11 once, right? So once we get to this 1, we're finished with the process of prime factorization. So on the left here, or prime factoring I should say, on the left here we have the prime factorization of 132. So we can see some of the ways we can get 132. For example, we know of course there's 1 times 132, the trivial factorization. But then we also notice there's 2 times 66, right? 3 times, see, 2 times 2 is 4 times 11 is 44, right? But none of those are doing us any good yet, because we're trying to look for two numbers whose product is negative 132, but whose sum is positive 1. So that means these two numbers have to be pretty close to each other, so that with the adjusting of the signs, we can go ahead and get a 1 out of them. They need to basically be within 1 of each other. So we need to be looking for slightly larger possibilities, right? So now we'll start grouping a little bit more differently, meaning in the sense that we'll include more numbers. So like, how about 2 times 2 times 3? That's going to give us 12 times 11. Now that looks promising, doesn't it? Because we were looking for two numbers whose product is negative 132, but whose sum is positive 1. So we're going to have a negative number and a positive number. That much we know for sure, because that's the only way the product of two numbers can be negative. And of course, since we want a positive sum, we're going to make the bigger one positive and the smaller one negative. Now we look and we notice that the product is negative 132, as we can see here. 2 times 2 times 3 is 12 times 11. We know that's 132. And their sum is positive 1. So that's perfect. So we have x minus 11 times x plus 12 equals 0. So we get x minus 11 equals 0. We're applying the 0 factor property now. Or x plus 12 equals 0. So this one gives us x equals 11. This one gives us x equals negative 12. And this is where the path between solving just a simple equation and solving a word problem, a real life application, part ways, because actually here we left the 1 out, so that's 11, not 1. So the reason being, if this were not a real life application and we weren't dealing with a real post office, we would have accepted both of those solutions as we did in the previous lesson. But here, at least I have never been to a post office which uses negative numbers on its post office boxes. So we're only going to be able to accept this as a reasonable solution. So if this is the only reasonable solution, and that means the first box here is numbered 11, and for the next one, I'm just going to have to take that 11 and add 1. So I get 12. So now we'll answer the question. The number written on each box, 11 and 12. All right, so that's just a very quick, simple, but interesting application, given that it gives us plenty of useful practice. All right, let's look at another one. Before we go to the next one, though, remember, this is an example of what we call consecutive integer problems. It falls into that category, because even though it wasn't said in exactly those words, we knew that whatever these values are going to be, they're going to be 2 consecutive integers. All right, for our next example, we are trying to help Vincent, who wants to build a miniature golf course in his backyard that is 4 feet longer than it is wide. And we want to recommend the dimensions of a golf course to Vincent that would make best use of the 77 square feet of planting material that he has, materials that he has purchased. So as far as understanding the situation, we're basically dealing with a rectangular plot that Vincent wants to build. So we know that he would like one side to be 4 feet longer than the other. So usually we call the longer side of a rectangle its length, and the shorter side its width, right? So this is what we call, this is an example of a group of problems called comparison problems. Why? Because we're comparing one thing to another. So you want the length to be 4 feet longer than the width, right? So if you think of that phrase right there, the last name that you see is basically the width, right? So usually we'll go ahead and call that the unknown x. It'll be easier to set this one up if we give that a name first. So this one is just going to be whatever that is plus 4, right? So we have the width and the length. We want x here and x plus 4 there. Now, we're also told that basically what the area should be, because that's how much planting material Vincent has purchased. So to use all of it up, we're gonna go ahead and make the amount of purchase the very amount of the field that we're going to create, the green field. So we're going to let the area of the field be 77. And if we replace the area with what it is, notice it's length times width. So we can just write x times x plus 4 or x plus 4 times x, makes no difference. Easier to write the x first. So x times x plus 4 equals 77. So now we're just going to go ahead and simplify and solve. So x squared plus 4x minus 77 equals 0. So we go ahead and factor this. X, right? 77. So 11 and 7 sound pretty promising, right? Because if we make this positive and this negative, notice first times first is first, last times last, pay attention to the signs, is last. Inner product is positive 11x, outer product is negative 7x. When you combine them, you get positive 4x. So this should be good. So we have x plus 11 equals 0, or x minus 7 equals 0. So we have x equals negative 11 or x equals 7. Again, if this were just a purely mathematical equation we were asked to solve, right? Somebody just gave that to us and said solve this like we did in the previous section. Then we would have actually provided two solutions. But because we're dealing with a real life situation and this has to be representing the width of an actual rectangle, we cannot have a negative width. So we'll reject this solution and we'll only accept this one. So it's a mathematically perfectly good solution, but it's not a realistic solution because we're dealing with a real plot which has to have a real positive width and a positive length. So now look, that's why I created this table here. Now you can just go in here. You know what x is? X is 7. So length is going to be 7 plus 4, which is 11. So the dimensions should be, normally with a rectangle we write length by width. So we say 11 feet. Remember, we always include the units for our final answer. We put a cross, we say 11 feet by 7 feet, like so. All right, so straightforward and simple, but make sure you can carry it out on your own without any help before you proceed. So what you do is you back it up, back the video up. Let me show you how. Or you cover all of this to where all you see is the question, and you try to do everything else on your own. That's how you make sure that you really understood it without any peeking, right? Then you should be in good shape. So this next problem is a clearly consecutive integers problem, and it's not hiding that fact either. So we have the product of two consecutive integers is 16 more than twice their sum. Find the integers. All right, so what's really helpful, I find, for this kind of a problem is to do a quick small table. So here we have a first integer and then the second one after it, right? So remember, when you're dealing with consecutive integers, it's like numbers like 3, 4, 5, or like -10, -9, -8. Yes, you can have negative integers. Or like, for example, -1, 0, 1. You can have, those are 3 consecutive integers as well. No matter that what the first one is, let's call it x, the next one, notice, is always going to be one more. So to get 4 from 3, you add 1. Now the next one, if I don't want to bring in a new variable, I'm just going to add 1 to that. So x plus 1 is the same as x plus 2, etc. So this relationship is always going to hold when we have consecutive integers, right? So if the first one here is x, the second one is just going to be x plus 1, right? So what do I know? I know that the product this is going to be an intermediate equation with words, all right? Is, which means equals. Now, when you see a phrase like this, 16 more than twice their sum, right? So ask yourself, what comes after more than, right? Notice I'll underline it for you. Twice their sum, right? So what you're going to do is write whatever it is that comes after more than or less than first. So twice their sum, so I'm just going to put that like this. 2 times their sum, right? That's twice their sum. Now, this product is what? Is 16 more than this, right? That means what? That means add 16, like that. All right. So now it's going to be a very simple matter to try to come up with the equation, because we know what product means. It means multiply. So the product of these two integers. So x times x plus 1. Remember, at any point where you have that aha moment, you're like, oh yeah, I got the rest. I know where this is going to go. Then you should pause the video and continue on your own. Then come back to see if we agree. All right, so twice the sum. So that means 2 times. Now, what is sum? Sum means the result of addition, right? So you're going to add these two integers now. So you're going to have x plus 1. See, that's their sum, that's their product. X times x plus 1, product, x plus 1, sum. We don't really need parentheses because we're adding here. And then plus 16, right? So we end up with x squared plus x is equal to, now it's better if we combine those two x's inside the parentheses first. So 2x plus 1 plus 16. So we get x squared plus x equals 4x plus 2 plus 16. So x squared plus x. What you want to do is always fully simplify each side first before you move anything around, okay, from one side to the other. That's the safest way to fly. So now we're going to go ahead and move everything to the left side and just leave a 0 on the right side. So we have x squared plus x, subtract 4x from both sides. That's going to move the 4x to the left side and make it negative. And subtract 18 from both sides. That's going to move the 18 to the left side and make it negative. So we end up with this. So we have x squared minus 3x minus 18 equals 0. So now we go ahead and factor again. So we have x, and I believe negative 6 and positive 3 should do the job, right? See, x times x is x squared, negative 6 times positive 3, last times last is last. Negative 18, the inner product is negative 6x, the outer product is positive 3x. Together they give negative 3x, which is what we want, and that should be good. So we get x minus 6 equals 0, or x plus 3 equals 0. So this one gives us x equals 6, this one gives us x equals negative 3. Now, notice that they didn't tell us the integers have to be positive or negative or even or odd. They didn't give us any such restrictions. So that means here we're going to have two possibilities. See? This is a pure number problem. These aren't numbers associated with any real entities where we have to be worried about them not becoming negative or anything like that. So here, let's go in this table we created in the beginning, which is going to be nice for this step as well. So we're going to go ahead and write that if x is 6, notice the first number is 6, the second one is going to be 6 plus 1, which is what? 7. And if the first number is -3, the next one will be -2. -3 plus 1 is -2. So you want two consecutive integers. If 16 more than twice their sum, so the product. So here 6 times 7 is what? 42. And what is 16 more than twice their sum? Well, let's see. 6 and 7 is 13, right? Times 2 gives us what? 26. Add 16 to that and you get what? You get 42. So we're in good shape. We can try this one too. So their product is going to be +6, right? What's their sum? Their sum is -5. Double that, you get what? You get -10, and add 16, you get what? You get 6, which is exactly the same as their product. So you see how we have two possible solutions. So the number pairs can be 6 and 7, or -3 and -2. The way systems like my math lab work, for instance, you just type them in. This is much better. I mean, this is the proper way of presenting this solution. But the computer technology, you know, you have to kind of come up with some way to deal with it. So what they do is they just type it in. So let's say you want to type this in for my math lab. You would just go 6, 7, -3, -2, like that. And the system should accept that. All right, so a nice problem. Make sure that you can handle this completely on your own before we proceed. All right, so if you notice here, we have another consecutive integer problem, but this time we're dealing with consecutive odd integers. So let's look at some examples of consecutive odd integers, like maybe 3, 5, 7, right? Or you can have -25, -23, -21, etc., right? So note the fact that whatever the first one is, the second one, the next one here, is not just going to be one more, is it? It's going to be two more. So the next one will be x plus 2, and then the next one will be 2 more than that. So it's going to be x plus 2, which is x plus 4. So in general, we have that relationship. So here we only have 2. So let's just call the first and second and create a table like we did last time. So this time we know that if the first one is x, the next one is not going to be x plus 1, it's going to be x plus 2. So it says the product of two consecutive odd integers, so two numbers like that, x and x plus 2, is 17 less than 4 times their sum. You should be able to set this up and finish this now. So for your own sake, pause the video, go finish this problem, and then come back. All right, welcome back. So the product of two consecutive odd integers, so we know how that goes, x times x plus 2, right, translates into equals, right, 17 less than 4 times their sum. Remember what we said? If you have a phrase like less than or more than, see what comes after that. So here, 4 times their sum is what comes after it. So you start with that, then you put minus 17, right? So 4 times their sum, right? So 4 times, what's their sum? Just add them. So x plus 2. But this time, 17 less than that. So that's why you go, oh, we left an x out. Let's fix that. So x plus 2. And then we know that this product is 17 less than this expression here. So we have to go minus 17. And that's it. Now we just solve it. So we get x squared plus 2x equals 4 times 2x plus 2 minus 17. So x squared plus 2x equals 8x plus 8 minus 17. So we have x squared plus 2x equals 8x minus 9. Now we have both sides fully simplified. We'll go ahead and move everything to one side. So x squared plus 2x minus 8x plus 9 equals 0. So x squared minus 6x plus 9 equals 0. This time we do have a perfect square trinomial. So that's only going to give us one solution, isn't it? Namely, x equals 3. So if the first one is 3, the second number is what? 3 plus 2, which is 5. So as a solution, the numbers are 3 and 5. Those are the two consecutive odd integers whose product is 17 less than 4 times their sum. And it's a very, again, straightforward, but it takes some getting used to. Make sure you can handle it completely on your own before you move to the next problem. And that is the great power of the pause button. All right, so here's an example of what we refer to as a Pythagorean application. Here we have two ships that sail from the same port at the same time. So in other words, you have some port and two ships take off. One named the North Star sails northward. So that means goes straight up, right? And the other one, called the Eastern Tiger, goes eastward. After 3 hours, the Eastern Tiger is 17 miles further from the port than the North Star. So we're going to make this one a little bit longer, right? And so we know that they left at the same time and they've traveled. So at this moment in time, right, they've traveled for 3 hours, and this ship, the North Star is here, and the Eastern Tiger at this point is here. And here is the port from which they both took off, right? And notice that this will be a right triangle here, because one went exactly north, the other went exactly east. Like so, right? It says, we know that at this point in time, this distance is 17 more than that distance, right? And it says the distance between the two ships is 18 more than the distance between the North Star and the port. So it looks like we're going to be using this distance twice. One in comparison to this side and once in comparison to that side. So this is a Pythagorean application, but if you think about it, it's also just another comparison problem. So which we utilize Pythagorean techniques to solve. All right, so if we call this side here x, we know that this side here is going to be x plus 17, because we know that after 3 hours, however much distance the North Star had gone, the Eastern Tiger had gone 17 miles more than that. And the distance between the two ships, so this distance, right, the hypotenuse of this right triangle is 18 miles more than the distance between the North Star and the port. So whatever that distance is, plus 18. So you want to find the distance of each ship from the port. We want to know this distance, we want to know this distance, as well as the distance between the two ships. So we need to know that distance as well. So of course you know that the Pythagorean tells us, theorem tells us that if you have a right triangle, and we used to use the letters A, B, and C, but since that can get you in trouble, and I'll tell you how, in this manner. For example, if this is A and this is B and this is C, and you're used to just thinking A squared plus B squared equals C squared, you would be incorrect, because in this triangle, it's actually B squared plus C squared, which is A squared. This would be incorrect. So because we want to avoid that kind of error, we don't, at least I don't even use the letters A, B, C anymore. So what I use is a little bit safer. I just say leg 1, leg 2, because remember, the two sides of a right triangle that form the 90-degree angle, this is called the right angle or the 90-degree angle, they are called legs. And the longest side, which is opposite the right angle or the 90-degree angle, is called the hypotenuse. So we can use H for that. So according to the Pythagorean theorem, the sum of the squares of the two legs is the same as the square of the hypotenuse, okay? So here we are going to get the fact that x plus 18 squared, so let me just put the hypotenuse squared on one side, is going to be the same as x squared plus x plus 17 squared. You see that? So now we're just going to expand and simplify. Now, be very careful with these. Make sure you don't just go x squared plus 18 squared. You know better than that, right? So you know that you can use either a formula, the f plus l squared formula, which is what we'll do here. It's the fastest way to fly, which is f squared plus 2fl plus l squared. So the square of a binomial formula, special product formula from the section where we covered that. So we get first one squared, so x squared, plus 2 times the first times the second. So the product of these two is 18x, and then times 2 will give us 36x. Plus 18 squared, which is 324. On the other side, we have x squared plus, now we're going to apply the same formula to x plus 17. So we get x squared plus, now when you multiply these two, you get 17x, and then double that, 2fl. So you end up with 34x plus 17 squared, which is 289. So now there is one clear simplification with C which we cannot pass up. Remember, anytime you have exactly the same term on both sides of an equation, remember, when we say exactly the same, that means they have to be not only identical but have the same sign. So they can't be opposites or anything like that. But they have we have the exact same term, we can just subtract it off from both sides, right? Which means it just gets canceled out. So those are gone. That'll make things a little bit faster and easier. So we end up with let's go ahead and move everything to the right side. So we get 0 equals x squared plus 34x plus 289 minus 36x. We bring the 36x over, it becomes negative, and then minus 324. So we get 0 is equal to x squared, 34 minus 36, that's negative 2. So minus 2x, 289 minus 324. So 9 from 14 is 5, 8 from 11, so 35. So we have, and that'll be minus 35, right? Like so. So x squared minus 2x minus 35 equals 0. So, and then we go ahead and factor the right side. That should be pretty simple, actually. X minus 7 times x plus 5 should do, right? First times first is first, last times last is last. Inner is negative 7x, outer product is positive 5x, which add up to negative 2x. We're good. So now we're going to apply the zero factor property. So we get either x minus 7 is 0 or x plus 5 is 0. So that means either x equals 7 or x equals negative 5. Keep in mind what x is. X is the distance between a port and a ship that has left it 3 hours before a given time. So negative 5 is out because distance can't be negative. So we reject this one. And now if x is 7 miles, that means the North Star is now 7 miles, has gone 7 miles in those 3 hours. X plus 7, that's going to be 7 plus 17, 24 miles. And x plus 18, 7 plus 18. So the distance between them is now 25 miles, okay? So there's a nice simple application for you to try as well. It involves basically a comparison scenario together with an application of the Pythagorean theorem. So a nice combination. All right, and of course, quadratic factoring techniques. So make sure that you understand that and then join me on the next problem. All right, here's a problem that a lot of people find scary, but it's really not that bad once you just relax and read it. When an object is projected straight upward into the air from an initial elevation h0 with an initial velocity v0, then its height from the ground t seconds after being thrown up can be found using this quadratic model. All right, these are basically the works that Newton left behind. And this is something you would find in a physics class. So h of t equals 1/2 gt squared plus v0t plus h0. Here g is negative, basically the acceleration of gravity, which is negative 32 feet per square seconds. And it's moving downward, that's why the negative sign. Suppose a ball is thrown into the air from the top of a lighthouse 48 feet above the ground with an initial velocity of 32 feet per second. So here we're given that the initial height, so we have some kind of a lighthouse, right? And we throwing the ball straight up from the lighthouse, right? So the initial height is 48 feet, and the initial speed is so v0 is 32 feet per second, and this was h0 right here, right? So basically, this formula h of t equals 1/2 gt squared plus v0 t plus h0 is going to turn into 1/2 h of t equals 1/2. Remember, g is -32 t squared plus v0, which is 32. Remember, these 32s have nothing to do with each other. It just happens to be that way. This is 32 feet per second. That one is -32 feet per square second. Very different. One is speed, the other is acceleration. All right. So plus 32 t, and then plus h0, which is 48. Remember, the lighthouse was 48 feet above the ground. All right, so if we simplify that, we get h of t equals -16 t squared plus 32 t plus 48. All right, so after how many seconds will the ball be at a height of 64 feet? In other words, they're giving us the height, h of t. They want us to find t. So we just substitute 64. So we get 64 equals -16 t squared plus 32 t plus 48. And I notice right off the bat that 16 goes into every one of these numbers. So it'll be really nice if we can go ahead and just get rid of it right away. So we're dividing both sides by 16. Then on this side, because it's a sum, it splits up like this. So we might as well just write 16 under each term, right? So we end up with 64 divided by 16 is 4 equals -t squared, because these cancel out, plus 32 over 16 is 2t plus 3, right? Let's go ahead and move everything to the left side. Notice the t squared has a negative coefficient, so it's better to just take it to the left side. So we get t squared minus 2t minus 3 plus 4 equals 0. So t squared minus 2t plus 1 equals 0. So if we go ahead and factor that, we end up with t minus 1 times t minus 1, see? So we don't need to set it equal to 0 twice. We know we're just going to get one t value, and that's 1. So it takes 1 second for the ball to reach a height of 64 feet. All right, one nice thing about technology, it lets you just move things. I moved this to the right a bit to get room for these. So when will the ball be... Okay, I can see a typo here. I meant 60. So let me change that. So after how many seconds will the ball be at a height of 60 feet? So this time, we're going to start with the same equation, h of t equals -16 t squared plus 32t plus 48. And we're going to replace the h of t with 60. So we get 60 equals -16t squared plus 32t plus 48. So now, again, we can see that at least 2 perhaps, can we do more than 2? Yeah, I believe we can do 4. At least 4 goes into all the terms. So we can divide both sides by 4. So we end up with 15 equals negative 4t squared plus 8t plus 12. Moving everything to the left side, we end up with 4t squared minus 8t plus 3 is equal to 0. Because we had 15, we bring over the 12 becomes negative 12. So 15 minus 12 is 3. So now if we go ahead and factor this, let's try 2t and 2t, maybe 3 and 1. And I do believe they both need to be negative. So let's see. First times first is first. Yes, it is. Last times last. Negative 1 times negative 3 is positive 3, which it is. The inner product, let me change that so it doesn't look like it's an equal sign. Okay. So the inner product is negative 2t. The outer product is negative 6t. And they add up to negative 8t. So we have it down correctly. So now we set each one equal to 0 by the 0 factor property. So we get 2t minus 1 equals 0 and 2t minus 3 equals 0. So 2t equals 1, t equals 1/2, or 2t equals 3, so t equals 3/2. Now, it looks like both of these answers are fine, right? There's no technical reasons why they can't be both answers be correct. So what gives? How can that be? Well, think about it. Notice that this ball is going to go straight up. Obviously, it's not going to go on forever. It's going to reach some maximum height. Then it's going to start falling back down, right? So it goes on up and then it falls right back down. I drew it a little bit separately just to show what's going on, but that's what's going on with the trajectory of the ball. It's going to go straight up, stop, fall straight down, right? So notice that every height other than that maximum height, the ball is going to reach twice. Once on the way up, once on the way down. You see that? So that's why it makes sense. So notice it reached 64 only once, right? That tells you 64 must have been that maximum height. But 60 must be somewhere along the way, maybe around here, right? So it reaches 60 twice. Once on the way up, it'll reach 60 feet, and then once again when it's falling back down, it'll be at a height of 60 feet. So that's the reason why both of those times make sense. And of course the units are seconds. Obviously the shorter time is the one corresponding to the way up. The longer time is corresponding to the time where it's reached the max point and then come back down to reach the 60 feet height again. All right, so when will the ball hit the ground, right? That is assuming this is going to go up and it's going to fall independent of the lighthouse and go back all the way to the ground. So in other words, I'm going to erase this part here now that we're finished with it. All right, so now we can see that we start with the same formula or equation. We have h of t equals negative 16t squared plus 32t plus 48. This time we want to know when the height is going to be 0. That's where ground is, right? At height 0, elevation 0. So we get 0 equals negative 16t squared plus 32t plus 48. This time notice 16 goes into all the terms, right? So, but I would like to have a t squared which is positive, so I'm just going to divide both sides by negative 16. Remember, we're not dividing the right side by negative 16 3 times. We're only doing it once, but then it splits up, right? So that's why we write it 3 times. All right, so 0 divided by negative 16 is just 0. On the right side, we get t squared minus 2t minus 3. So now we go ahead and factor the right side. We end up with t minus 3 times t plus 1. We do a quick check. Notice I'm trying to practice what I preach. I always check. First times first is first. Last times last is last. Inner product is negative 3t. Outer product is positive t. So we end up with negative 2t. So we have either t minus 3 equals 0 or t plus 1 equals 0. So we get t equals 3 seconds. Or t equals negative 1, which of course time can't be negative. We reject that. So for part C, your answer is going to be here. This one here was, these here were for part B. And of course, the original one that I erased with t equals 1, that was for part A. All right, so this ball is basically goes up for 1 second and then falls back down. All right, so that should do it for this problem. Notice it looked a little bit scary, but once you get to know it, it shouldn't be that bad. You got to practice them a few times till you become really comfortable with this kind of problem. And then you've suddenly left who you were logically before a problem like this behind, because now you're somebody else. You're a more logically advanced person. And every time you solve a new level of mathematical problem or any kind of problem engaging you logically, that's what happens. You're no longer the same person that you used to be. All right. All right, here's a really simple problem that, again, looks kind of scary, so I just wanted to introduce it to you. The following data provided by the Wireless Association, which is known as CTIA, shows the number of cellular phone subscribers in the United States. Okay, so in 1994, there were 24 million. In 1996, it started going up quite fast, right? 1998, 69, etc. So remember, these are in millions, right? So it says this data can be used to develop a model, right? So a mathematical model where you can estimate, give them a year, give the model a year, and then it'll estimate the number of subscribers, right? So the only reason I wanted to introduce this problem to you is because you'll see this kind of question in statistics, for example, quite a bit. And here, X is not actually the year that you're going to plug in. X, to make things simpler so that you plug in a smaller number, they set up the model so that X represents the number of years basically after 1994, right? So what does that mean? That means, for example, in 1996, X would be represented by 2, because you just want to go 1996 minus, so this is going to be the base year, right? So you want to know what X is for the year 2002, easy. Just subtract, go 2002 minus 1994, subtract 1994 from 2002, and you'll get your answer. Okay, so you'll get what? 8. 4 from 12 is 8, right? So like so. So using this model, estimate the number of subscribers in the year 2000. So 2000, we want to know what X is, right? So in 2000, X is going to be 2000 minus 1994, right? Which is what? 6. So now we know the X value that we have to plug into that equation. So we're trying to find C of 6, which is going to be 0.347 times 6 squared plus 13.14 times 6 plus 17.98. Now it's just a matter of computation. So we'll just plug it in. So you just have to make sure you have the numbers correctly. 0.347, 13.14, 17.98. We should be good to go. So 0.347 times 6 squared, which is 36, plus 13.14. Okay, I didn't register the point. All right, times 6 plus 17.98. Now we hit enter. We get 109. So let's go ahead and approximate that. So approximately 109.3. So approximately 109.3. And of course, remember, that's in million. So according to the model, it should be around that many million, right? So now we want to see how that result compares to the actual value from data. See, very, very closely related to that. These are actual numbers from the association. Okay, so using this model, estimate the number of subscribers in 2008. So you're going to do exactly the same thing. In 2008, X is going to be whatever 2008 is minus 1994. Remember the number of years since 1994. 4 from 8 is 4, and 9 from 10 is 1. So 14. So we're just going to repeat the same process. We're just going to replace 6 with 14. So we get C of 14 equals 0.347 times 14 squared plus 13.14 times 14 plus 17.98. If you remember the trick on most modern calculators, you can go and select that, hit enter, and then go replace. So we can go to 36 and replace it with 14 squared, and we can go to the 6 here and replace it with 14 and then hit enter, and we get approximately, where did you go? Approximately 270, let's say, approximately 270 million, right? Now, how does that compare to the results from the table? It's starting to become a little bit distant from the actual numbers, right? And that happens with these models. They do better toward the center of the model where the computations were more accurate. So, and assuming the trend in the table continues, use the model to estimate the number of subscribers in 2013. So notice that we're going to do the exact same thing. In 2013, x is going to be 2013 minus 1994. So, which is, I believe, let's see, 2013 minus 1990. Okay, let's go fix that. 13 minus 1994. We end up with 19. That's what I thought. Want it to be safe. All right, so now, okay, by the way, here, what I meant was C of 14, so I left the opening parentheses behind there. So now we're going to find C of 19. So you know what that means, 0.347 times 19 squared plus 13.14 times 19 plus 17.98. So again, we can go and copy this last result and replace the 14 with 19. This can save us quite a bit of writing, okay? And then go back and replace that other 14 here, the second one, with 19 as well. And then hit enter, and we get approximately 393 million. Now this one is quite unreliable because things can happen. Notice that 2013 falls outside of the range of these years for which we have actual data. So we call this extrapolating. This is something you want to avoid. It's okay if you don't have some years in here like 2003. It's perfect to, I mean, perfect. It's really pretty safe to use this model to approximate a value for that year. But years that fall outside the range, either after 2010 or before, it's going to be very unreliable because events could have taken place to change this trend, either dramatically toward the upper or lower, which actually happened in that direction. They went up really fast after that. All right, so there is another application, and that should do it for today. So make sure you practice these and stay safe until our next video.